All right, so as we recall and try to retrieve these calculus principles that are going to be necessary for learning dynamics this semester, I'd like to start you off with a nice little problem. So imagine having a water tank. So here's my water tank right here. The water tank has an inlet and an outlet. The inlet is where water is going to be flowing into the tank. And let's suppose Qn is the amount of water coming in. So Qn is going to be measured in quantities of liters per second. Liter is a volume. Liters per second is a volume per second flowing in. Right? Q out would be the rate of flow going through the outlet. Again, liters per second, volume per second coming out of the tank. And then what I'm going to do is I'm going to define this Q, which is Q in minus Q out. So if Q in is bigger than Q out, we have more flow going into the tank than going out, right? Q in minus Q out is the net flow in, right? So when Q is positive, I have more going in than going out, right? When Q is negative, then I have more flow going out than coming in. So the net flow into the tank would be negative in that case. Now what I'm going to do is we're going to have a plotting exercise, and I'm going to give for you a plot of Q. So this is the net flow into the system or into the tank as a function of time, right? So initially we've got this much Q and then it bumps down here, and so forth. And what I want you to do for me is plot the volume of water in the tank. Okay, so this little dot on the v-axis here at t equals 0, that's going to be the initial volume of water. So that's where we're going to start off. And what I want you to do is plot for me the volume as a function of time. I put these vertical little dashed lines here so that you can line up the time axes on the two plots appropriately. All right, so if you haven't done that, go ahead and do that right now. Don't see my solution. I want you to try it on your own. In the description for this video, there will be a link to the PDF where you can find this particular document. All right, go for it, and then once you have your graph, come back.
Olha que coisa mais linda, mais cheia de graça, ela menina que vem e que passa, doce balanço, caminho do mar.
All right, now I'm assuming that you've worked through it on your own. And as we go through it, what I'd like to do is refer to a student's answer that I have right here. So here's something that a student submitted to me. The student, I think, did a pretty good job. I think obviously a lot of thought went into this, but what I'd like to do is examine this thing more closely. And what we're going to do is start at the very beginning here. So let's just look at this first segment right there. In this segment, the Q, the net rate of flow into the system, is positive and it's constant. So what do you think? Is this part of the student's solution correct? Yes or no? If it is, why does it make sense? If no, what's wrong with it? All right, presumably you've already worked this out, but maybe you can think about it for another second, and when you're ready to discuss it more, start the video again. All right, so let's discuss this. The Q is the net flow rate into the tank. Let's just put a concrete number on this thing. Let's suppose it's 5 liters per second. Okay, 5 liters per second coming in. And it's a constant 5 liters per second for a little while, right? So what does that mean? The volume is going to start off here at some volume of water inside the tank, and it's going to increase at a rate of 5 liters per second. So 1 second later, it's going to have 5 more liters in the tank. 1 second after that, it's going to have another 5 liters in the tank. A second later, another 5 liters in the tank. Maybe a little higher there. Right? Every second, the tank gains 5 liters of water. That volume of water keeps on increasing and increasing along a straight line, right? It's increasing at a constant rate so that the volume of water in the tank is just sort of growing linearly. So we have a straight line with positive slope whenever the Q is a positive constant. All right, now let's go back to the student's solution. So here we are. I think the student is saying the exact same thing, right? Volume grows at a constant rate. We are in agreement. All right, so let's reveal some more of the student's solution. We'll keep on going in time, so maybe right here is a good time. All right, so now the student is saying that just as the time reaches this dashed line right here, maybe slightly before it reaches this dashed line, the student notices that the Q is dropping, and the student says at the same time, therefore, the volume of water in the tank must be dropping as well. So what do you think about this? Does this one make sense? Pause the video, think about it, compare it with what you have, and see if we can make an argument. All right, so let's think about this. So after the first dashed line here, what's going on? So we notice that Q starts decreasing, right? Q starts decreasing, but Q is still positive in this segment right here, yes? So in this segment, this means that more water is flowing in still than flowing out, right? The tank is still gaining water in a net sense. There might be some flowing out, but there's still more going in than going out. So therefore, the volume of water should be increasing in the tank, right? The student's solution says it's decreasing. Oh, that's a contradiction. Since Q is positive here still, this volume should still be going up. It might not be going up as quickly as it was before, so it'll sort of bend down a little bit. But I'm thinking that volume should still be increasing in this interval. Whoa, how about that? The next interval, maybe this purple interval here, right there, that interval, during that interval, now we see the Q start to decrease, see the Q start to go negative. Right? So once Q passes through 0 onto the negative side, that means more water is flowing out than flowing in. So what does that mean? This means when we're at this time where Q goes through 0, that's when the volume of water in the tank reaches its maximum. Because after that time, after this time right there, then we've got more water flowing out than flowing in. And this thing should bend over. So again, the volume reaches its maximum right here, and just past that maximum, when Q becomes negative, volume decreases. We get a local maximum in the volume of water right at that point where we have the crossover on the Q. How does that sound? Get this concept in your head. This is really important right here. The maximum volume of water in the tank happens where the Q, the flow rate, passes through 0. All right, let's continue this a bit farther. We'll look at it all the way up until this vertical dashed line right here. And the student's solution looks like the water is draining, right? Like so. How does that look to you? Again, think about it for a moment before we talk about it. Obviously, the curve is not supposed to be down here. It's supposed to be up here at this point. But I think the student is suggesting that, at least from here, we should have the volume decreasing steadily, it looks like. Yeah, that's the proposal. How does that sound? Well, I'm thinking this makes a lot of sense, right? Q, the net flow rate is negative. That means more water is coming out of the tank than going into the tank, right? So the total volume of water in the tank should be decreasing, right? And now it should be decreasing at a constant rate, right? This might be minus 1 liter per second, maybe a little less if that's 5 up here. And so each second, 1 liter drops out. So I'm thinking this volume should be decreasing along a straight line like so. What do you think? Does that make sense? Let's make sure it makes sense before you go on. Well, I think there's something wrong with my line. Do you see it? Do you see the mistake that I made? There's a mistake in here. See if you can catch it. Where's my mistake? Well, notice that the flow rate coming out in this interval is much smaller in magnitude than the flow rate going in that first interval, right? In that first interval, we see that the volume in the tank rising rather rapidly, and then I have it falling just as rapidly. But the flow out during this interval right there is much smaller than the flow going in this first constant integral up here. So this line here should not be as steep. So in actuality, I'm thinking this curve, I'm thinking this drop in volume should be much shallower, right? Not as steep as the increase in volume, much shallower. We got a smaller flow rate out of the tank than we had going into the tank. Now I think I'm happy about this. Okay, moving on. Next I'd like to consider this interval of time right here. What's going on there? Well, we see a rather dramatic change in the flow rate, right? It was up here and then poof, the bottom dropped out of it. All right, so let's see what our student did. Our friend, now that's interesting, isn't it? That's kind of curious, actually. What we see is a jump in the volume, right? At one instant, the volume's up here, and then all of a sudden it jumps down. And this jump in volume seems to correspond to this jump in the Q. The flow rate, the net flow rate. Does this drawing down here make sense? Can't think of it. Here's the proposal from one of your classmates. I think it's really interesting to think about. Well, the only thing this jump means is that the flow rate out of the system increased dramatically, right? Doesn't mean the volume decreased dramatically. It means the flow rate decreased dramatically. It means all of a sudden flow is leaving the tank at a greater rate. The fact that this thing was sloped down right here we have negative Q. The fact that this thing is sloped down means it's leaving. And then at this time, if it starts leaving faster, well, that just means the slope is steeper. This line, this volume curve, is now going to be coming down at a much steeper rate, like so. What do you think? This jump in the Q corresponds to a little kink in the volume curve, right? So for a while, this volume curve has a slope downward, and then all of a sudden, there's the kink, little sharp corner there. This sudden change in slope is the result of that jump in the flow rate. Now things are kind of taking shape. Do you see how these pieces are fitting together? All right, now before we go on, I'd like to go back a little bit, if you'll let me. Let's go back to this first interval right here, where Q was this constant positive number. In that case, we had flow of water pouring into the tank. And I think we hypothesized there might be 5 liters per second going into the tank, right? And let's suppose during this interval was, how about 25 seconds? Just to put some numbers on here to think about. So during that interval, how much would the volume increase? We've got 5 liters per second of water flowing into the tank for a total of 25 seconds. All right, so 5 liters per second times 25 seconds is 5 times 25, 125. 125 liters go into the tank at the time, right? So this jump in volume from there to there, that's 125 liters, yeah? And you can think of that 5 liters per second times 25 seconds, that would be the area under this curve right here. Do you see what's going on here? This change in volume is the area under the Q curve. That's curious. Now notice that the volume is still increasing after that, right? So what's happening during that second interval? Well, here the Q, the flow rate into the system, is decreasing. It's still positive, but it's decreasing towards 0. So the first second, you got just a little under 5 liters per second times 1 second. And then the next second, you got a little bit less q times that second, right? And a little bit less q times that second. And each one of those q times that second, that's a sliver of area underneath the curve. And I'm adding up all those areas under the curve to give me the total volume that went into the tank during the second interval. So the extra volume we got from that next interval, right here, is the area under this part of the curve. Do you see what's going on? The total change in volume is equal to the area under the Q curve. For this first two intervals, we got positive area, and then we start accumulating negative area, which is the amount that the volume is going to start dropping. And notice that this positive area right here is bigger than the negative area right here. So the net amount of volume gained from this time right here to this time right here is positive, right? I go from this volume all the way up to that volume. Hope this is sounding familiar. Area under the curve. Sounds like an integral, doesn't it? Once the floodgates open and water flows out at a faster rate, now we're accumulating more area. And we can see that volume dropping faster and faster. Eventually, there's going to be a time, perhaps this time right there, that's the time at which the volume returns to its original value. Geometrically, what does that mean? At this time, that means, let's say it's that time right there, that means the positive area under the curve up here is exactly balanced out by the negative area under the curve right there. So when these two areas, the area above the curve and the area below the curve, when those two areas equal each other, that's when my volume returns to its starting point again. That's where the net accumulation of water going into the system is 0. Beyond this time, I keep on accumulating this negative area and watch the volume dip below its starting point, right? The volume's going below where it actually started. Now I've got to be careful how I draw this curve. I drew it as a steep curve because that's a pretty negative net flow rate, right? But I got to be careful since this is a tank that this volume is the volume of water. I can't have negative volume of water, right? So I'm making sure to keep this curve above v equals 0. All right, I think we're ready to finish off this problem finally. So let's look at what your classmates said next. Next, this person said, well, actually, this person made the same mistake that was made earlier up here, right? So once the flow rate started picking up again, this person made the volume curve turn upward again. How should it go? Thinking about it, think about it. How should it go? Notice that the flow rate's negative here still, right? So there's more flow going out of the system than going into the system. So therefore, the volume should still be decreasing beyond this point right here. It should be decreasing all the way up until this time right here when the Q curve passes through 0 again. So this volume curve reaches its minimum at this time right here. Then the Q, or the flow rate, net flow rate into the system, becomes positive. So that's where this thing turns around and starts heading back upward again, right? In fact, it turns pretty quickly, right? Because this is a pretty short interval right there. And then it starts heading uphill again. Volume starts increasing again. And notice that it's increasing about the same rate that it was at the very beginning. So when this thing turns the corner and volume starts increasing again, the slope here should be about the same as it was when it was initially filling up. So I'm going to draw this curve kind of like this. And I think we're done with this plot. All right, so let's wrap up this video by just summarizing what we found. First of all, let's recall that this volume curve, we can think of it as the area under this flow rate, or the Q curve, right? Whenever the Q is positive, it would be accumulating positive area. Whenever Q would be negative, this thing would be accumulating negative area. So that relationship where one's the area under the curve of the other is an integral. So volume, integral of Q, and it's accumulation over time, right? So it's an area in this time plot. Maybe I'll take this and move it down here, because this one's the volume curve, right? And here we're interpreting the volume, again, in the normal calculus way, as the area under the Q curve. Another way we can think about it, especially it's sort of natural to think about it in this tank filling problem, is that the volume here is really the accumulation of the flow rate Q over time, right? As Q is positive, you're accumulating that flow rate to increase the total volume. So integration, we can also think of it as an accumulation. I like to think of it as an accumulation, right? It's a summation of all the Q that came before it. So that's how I worked out this plot, but we can think of it the other way too, right? We can think of this Q, the opposite of integration is differentiation in this case. So Q is the derivative, that flow rate is the derivative of volume with respect to time. And we kind of see that in the units, right? Q had units of liters per second, right? V, the volume, had units of liters. So liters per second is the rate at which the liters are changing every second. Makes sense? And you can see it in the plots too. Whenever Q is positive up here, V would be increasing. Whenever Q is negative, V, the volume, is decreasing, right? The more negative it is, the faster it decreases. Whenever Q passes through 0, V is at its maximum. Or over here we had Q passing through 0 and V was at its minimum, right? The derivative, whenever the derivative of something is 0, that's where it has its extrema. And we see it in these plots. So here we are plotting derivatives and integrals, and it's really important to know this relationship for dynamics. And that's where we are at the end of this video. Now that we are pros, though, I'm going to suggest you try another one. I've got it. So along with this initial problem I gave you, with the plots we just worked out, I also ask you on the second page to work through it the other way. Let's suppose the volume curve is given to you. Can you determine the Q curve? All right. You have to think the opposite way here, but I'm sure you can do it. And I'll save that solution for another time. Over and out.